The Milky Way alone contains hundreds of billions of stars, and it is an incomprehensibly massive, silent expanse. We have been listening to that deep space static for decades, waiting to hear something, anything that stands out from the background noise. In 1977, the Ohio State University Radio Observatory functioned as a massive aluminum listening post. Spanning 3 football fields and anchored firmly to the rural Ohio ground, the Big Ear spent its days waiting for radio waves to wash over its reflectors. Because the Big Ear was a stationary structure, it relied entirely on the rotation of the Earth to sweep its beam across the cosmos. At the speed our planet turns, a specific point in the sky would pass through the Big Ear's narrow observation window for a maximum of 72 seconds. This mechanical limit tells us exactly what a real, continuous transmission from deep space should look like. Over those 72 seconds, the signal intensity would smoothly rise, peak exactly at the center of the sweep, and gradually fade back to silence as the Earth kept turning. By locking the telescope's hardware in place, engineers created a precise mathematical trap. If an anomaly matched that exact 72-second bell curve, it couldn't be a random glitch. It had to be real. Back then, astronomical data was recorded as a stream of raw characters on massive stacks of line printer paper. Volunteers like Jerry Ehman had to comb through these columns by hand, looking for intensities that rose above the background noise. On August 15th, Ehman noticed a column containing a sequence he had never seen before, 6EQUJ5. In Big Ear's system, 6 was a moderate jump, but U was the highest value ever recorded, an intensity 30 standard deviations above the background noise. It was a massive, isolated surge of energy. The signal sat precisely at 1420 megahertz. This is the hydrogen line, a frequency naturally emitted by the most common element in the universe. Physicists had long predicted that if an intelligent civilization wanted to send a recognizable beacon, they would broadcast right on this channel. The signal lasted for exactly 72 seconds, displaying the precise bell curve shape required for a deep space source. And then it stopped. The Big Ear checked that same patch of sky repeatedly. Other global observatories joined the hunt, pointing their dishes toward the constellation Sagittarius. They found nothing. Humanity had recorded an incredibly powerful, perfectly shaped transmission, sitting precisely on the universe's most logical communication channel. And then the channel went permanently dead. To explain the mystery away, some scientists proposed natural causes. In 2016, a popular theory suggested a pair of comets passing through the beam emitted a cloud of hydrogen gas, tricking the equipment. Investigating this requires a look at Big Ear's hardware. The telescope used a dual horn design, scanning 2 slightly different patches of the sky side by side as the Earth rotated. Because comets move slowly, any hydrogen cloud they carried would have appeared in the first horn and then minutes later in the second. But the 1977 signal appeared only once. It was a single, sharp flash that never crossed the second horn. Every attempt to map a natural celestial body like a comet to the 1977 data failed. The signal's unique timing and intensity stubbornly resisted every conventional explanation we threw at it. When Big Ear was dismantled in 1998, its only surviving legacy was thousands of pages of raw data printouts. Today, these irreplaceable scientific records are stored in a private Ohio barn, where they are slowly succumbing to physical rot. In 2025, an international team began a race against that decay, digitizing over 75,000 pages of the observatory's records using optical character recognition. Converting these fragile sheets into high-resolution datasets allows computers to cross-reference the entire multi-decade record for the first time. The 1977 printouts only used a simplified 1:31 scale to represent intensity. By using modern algorithms to reevaluate the raw background noise levels, researchers found the original 1970s math was too conservative. The peak intensity didn't just hit the top of the chart. It soared to 250 Janskys, nearly 4 times stronger than the previous maximum estimate. This new digital precision allowed researchers to systematically rule out local interference. They confirmed the moon was in the wrong position to reflect radio waves, there were no satellites overhead, and solar activity was too low to interfere. Rescuing the physical data finally provided the evidence needed to settle the first part of the mystery. The signal was not a human glitch or a local reflection. It undeniably came from deep space. With local interference ruled out, we are left with only two possible suspects for what triggered the Big Ear. The first possibility comes from the Arecibo WOW project. They proposed the signal was a highly unique, naturally occurring event involving cold hydrogen clouds in the galaxy. Under this theory, a violent radiation source, like a magnetar, could strike an otherwise invisible cloud of hydrogen. This would suddenly stimulate the cloud, causing it to emit an intense, highly concentrated beam of radio waves on the hydrogen line. While a cosmic flare fits the chemistry, it struggles to explain the signal's narrow bandwidth. In astrophysics, natural energy usually smears across many frequencies. The WOW signal was incredibly narrow, a hallmark of an engineered transmitter. If it was artificial, its failure to repeat might be a matter of efficiency. A civilization wouldn't waste energy broadcasting a continuous beam in all directions. Instead, they would send targeted, intermittent pulses, meaning a follow-up signal might not hit Earth again for decades. We are still racing to find the truth within those decaying barn archives. Whether it was an impossibly rare cosmic flare or a brief 72-second greeting from the void, the WOW signal proves the universe is still waiting to be understood.